Hello students, welcome to JCE Connect series of lectures. So in this particular lecture I'll be solving some numerical problems on design of bending strength. So in previous lecture we have seen the how that is design of bending strength can be calculated, that we have discussed. So in this particular lecture I will be taking some numerical examples and you will be understanding in a better way. So let us take the first numerical problem, that is determine the design bending strength of a beam ISMB 300 at 434 Newton per meter. Use Fe 410 grade steel. So this is a problem given. They are asked determine the design bending strength. This one they ask is design bending strength, and so what is the first step we need to do here is, so we have to take the properties of ISMB 300, whatever the section is been given. So for that section you have to take the properties ISMB 300 at 434 Newton meter. So you have to refer the steel table. So from steel table you have to take the properties. So refer steel table and take the properties. Here I have taken, this is ISMB 300, this is ISMB 300. So this section is ISMB 300, and for this section I have taken the properties. H is 300, then the width of flange 140, thickness of flange as 12.4 mm, thickness of web 7.5 mm, then the root radius, this one. So this also you take this one, the fillet of the root radius, that is R1, is 14 mm. Then the modulus of section also you take, it is given in a steel table, so that also you take. Then I'll show you here for ISMB 300. Here for ISMB 300, this one ISMB 300, so this is 12.4, 7.5, that is the thickness of web, 12.4 the thickness of flange, and also you will be getting modulus of section, that is ZXX and ZYY. So you will be getting here, you can take ZE, that is this modulus of section is elastic modulus of section. These whatever the ZXX and ZYY are given, these section modulus are elastic section modulus. So refer this one and take. So here the elastic section modulus is taken 573.6. So here you will get 573.6 for ISMB 300, 573.6. So note it down. This one elastic section modulus 573.6, and plastic section modulus, either you have to calculate the plastic section modulus for the given section, or directly you will be getting from IS 800 2007 page number 139. So if you refer page number 139, you will get plastic section modulus. I'll show you plastic section modulus, page number 139. So here on page number 139, the given various sections here. Refer page number 139 of IS 800. See here. So here ISMB 300 is given. ISMB 300. So weight per meter 44.2. Then sectional area is given. Depth of the section, flange width, flange thickness, thickness of web, then radius of gyration, then the section modulus. Look at here. So section modulus given, both elastic section modulus 573.6 and plastic section modulus 651.74. It is given in centimeter cube. Okay, 573 and 651. So it is given in IS 800 2007. Refer IS 800 2007 page number 139. So you will get this plastic section modulus given in IS 800 2007 page number 139. It is 651.74 into 10 raised to 3 millimeter cube. Then the classification of section. So as you know, the sections can be classified as a plastic, compact, semi-compact and a slender section. So in which class the given section lies, where to calculate that one. So that's why we have to do the classification of sections here. So individual elements will lie in a different class. So we have to take the depth of web. How to take the depth of web as per the code we know, because we have solved some of the numericals on classification of section. You please refer that lecture. You will come to know how to take the D, that is the depth. So h minus 2 times of thickness of flange plus r1. Okay, so we have to take D from this point to this point. Okay, effective depth D. So that is, if this is the I section, D to be measured from here to here, depth of web. So that's why we have to deduct 2 flanges plus 2 root fillets R1. Okay, thickness of flange plus R1. So you'll be getting depth of web 247.2 mm. So next, after this one, next you have to calculate outstand flange width. As for the code, the outstand flange width will be B equal to half of the flange width. So this much we get. Then you have to calculate the ratios. The ratio of one ratio is B by TF, thickness of flange. This is one ratio, B by TF, 70 divided by 12.4, we get this much. Then another ratio you have to calculate, depth to thickness of web. Then this much we got. Then calculate epsilon, this one we get 1. Then as per IS 800 2007 table number 2, if you refer table number 2 page number 18, for a rolled section, the ratios, whatever the ratios are calculated, you have to compare with the limits given. So here the ratio is, in our case the ratio is 5.65, which is less than 9.4 epsilon. You want depth to thickness of web, which is less than 84 times of epsilon. In our case we are getting 32.96, which is less than 84 epsilon. Hence the section represents plastic section. Hence the given section is a plastic section. Now after classification we come to know that the section is plastic, hence we have to design it as a plastic section. So also one more check we need to do, the depth to thickness ratio, which is less than 67 times of epsilon, and that is also given in a code. So I'll show you here. That is page number 18 of IS 800. Page number 18. So here look at this page number 18, table number 2. Various classifications are given, class 1, class 2, class 3, and the ratios also given for a rolled section, width to thickness and the depth to thickness, and the various limits are being given. According to that you have to check. Then here what is being given here, web shall be checked for shear buckling in accordance to with 8.4.2 when D by T ratio is greater than 67 epsilon. So web buckling, okay, you have to check whether the web is resisting buckling or not. We have to check, and that check we have done here. So in our case we are getting less than 67 times epsilon. If we are getting more than 67 times of epsilon, we need to take the precautionary measures for web, hence web by providing a stiffness and all. In our case it is less than 67, hence there is no check for web buckling. That is, check for web buckling is not required, okay, because it is less than 67 times of epsilon. This is as per IS 18/2007. So after this, the next is the design bending strength. Then we have to calculate the design bending strength, that is MD to be calculated. So once we have classified the section classified as a plastic section, and for MD to be calculated, the MD value to be calculated is a list of the following two values. The first is this one, calculate the MD value, beta B ZP into Fi by gamma MO as per IS 18/2007, page number 53. Then where gamma MO is 1.1, beta is 1 for plastic section. This is for plastic section, beta is 1. And for Fe410 steel, Fi to be taken 250. Then substitute all the values in the above equation. Then we get 148.12 into 10⁶ Newton millimeter, or 148.12 kilonewton meter. And also this MD should be less than this value, that is 1.2 into ZE Fi divided by gamma M for a simply supported beam. This is for a simply supported beam, and we have got two values, that is 156.43. This is a 156.43 kilonewton meter. Another one is a 148.12 kilonewton meter. So whichever is the least, that is the design bending moment. So this is the design bending moment or bending strength, 148.12 kilonewton meter. I hope you understood this one. This is a very simple. So first we need to take this section properties, then section classification, then based on section classification, then you have to calculate the design bending strength. So let us take one more example, that is so we'll solve one more example here. Take one more example. Determine the design bending strength of ISLB 350 at 486 Newton meter. The design shear force is less than the design shear strength. The unsupported length of the beam is 3 meter. Assume the beam is laterally supported and steel grade is Fe410. So this is the problem given. So as usual, we have to get the properties of section given. From the steel table, you have to take the properties of the section. For ISLB 350 at 486 Newton meter, take all the properties of the ISLB 350. This is ISLB 350. This is the depth of the section, then width of the flange, then thickness of web, then thickness of flange. This is the root radius R1. So take all the properties from the steel table. So these are the properties I have taken from the steel table. H is 350, thickness of flange 11.4, and breadth of the flange 165, thickness of web all we have taken, and the root radius 16 mm. Then the elastic section modulus and plastic section modulus, you can refer IS 800/2007, page number 139. If you refer, you will get, I'll show you here. For ISLB 350, ISLB 350, so here is given ISLB, refer ISLB here, this one ISLB 350. For ISLB 350, the various properties are given here, you can refer this one. So here you will get section modulus, elastic section modulus, as well as plastic section modulus. So you can refer IS 800 2007 page number 139. So if you refer, so where the ZE is given 751.9 into 10 to 3 millimeter cube, and the ZP is also given. So both the properties you will get from the IS 800 2007. In steel table you will get only the elastic section modulus, but if you want to get the plastic section modulus also, you have to refer IS 800 2007 page number 139. So note it down both the properties, then do the section classification. So for that, take the depth of web, calculate depth of the web, and you know how to calculate the depth of the web. Again, just for the I section, this is ISLB. So from here to here is the depth of web. Okay, so you have to deduct thickness of 2 times of thickness of flange, 1 2 and 2 times of root radius. Okay, this much is the depth of web. Then next is outstand of flange. Outstand of flange, calculate outstand of flange, P equal to half the width of the flange, this much. Then I calculate epsilon, then calculate the ratios. Then the first ratios, that is width of flange to thickness. So this much we have got, which is less than 9.4, and the second ratio is this one, we got less than 84. Hence it represents the plastic section. According to IS 800 2007 table number 2, it represents the plastic section. Hence the section is classified as a plastic section. For a plastic section, beta is 1. This is also given in a code. Then since again we have to check whether the web is sufficient to resist the buckling or not. So check this one, D by TW is 39.9, which is less than 67. Hence check for shear buckling is not required. If we are getting more than 67, hence check for shear buckling is required. Then we have to provide additional stiffeners for that one. Then for laterally supported beam, design bending strength. Here the design bending strength is asked. So it is the least of the following values. The first one is this one. Then substitute all the values here. We got this much. That is, we get a 193.43 kilonewton meter. Then which should be less than for a simply supported. This is for a simply supported beam. For a simply supported beam, MD should be less than 1.2 ZE into Fy divided by gamma MO. Then substitute here, and you will get this one, that is 205 kilonewton meter. So whichever is the least in between these two, that is the design bending strength. This is the design bending strength. I hope you understood this one. So these are very simple. These are for how to calculate the design bending strength. So these problems are very simple. Only thing, just first thing is you have to take the properties of the section, then classify the section, then according to that apply the formulas, and all the formulas are given in a code book. Please refer a code, then solve the problems. Okay, so we'll continue with some more problems in next lecture. So here I'll stop. Thank you.